Hello guys, welcome to today's class continuation from the last class where we introduced separable variable differential equations. So let's apply what we learned from the last class. Remember in the last class we got once we separate the variable in this form, then we will be able to integrate both sides, y and the things associated with y, and x and things associated with x, and we are not going to forget to leave an integration factor. So I got this problem from engineering mathematics, K. Stroud, the 5th edition. So those of you who are lovers of K. Stroud like me, you can feel free to explore K. Stroud. It's really a good book for studying engineering mathematics. So let's dive into the solution of this problem quickly. So we're going to separate the variables. We have x into y minus 3 dy. The x is equal to 4y. So you will all agree with me that this equation can still be written as y minus 3 over 4y. Dy, the x is still the same thing as 1 over x. Okay, so we just separated the variables, took everything about y to the left hand side, usually then take everything about x to the right hand side. So y minus 3 over 4y is equal to about that. Dy is equal to 1 over x dx. Is that okay? So at this point, now that you've separated the variables, we can integrate. And after integrating, or after writing the integral symbol, now it's integrated, we can go ahead. I believe the challenge with most ODE problems is when it comes to the integration. That is why a strong prerequisite for understanding ordinary differential equations is you need to know your calculus very well, basics of calculus, differentiation and integration. So I hope as we solve along, we'll remember some methods to differentiate and integrate as we proceed. Now, looking at this particular place, this is how I'm going to approach it. So I'm going to distribute like this. I'm going to distribute this particular 4y to both y and 3y in this way. So we have y over 4y and minus 3 over 4y dy is equal to, when we integrate this, we'll get a ln x, okay, plus c. Then let's keep solving. So if we keep solving, we'll have integral of 1 over 4 minus, we have 3 over 4y dy is equal to ln x plus c. So if we solve on by integrating through, we're going to get 1 over 4, sorry about that, y on this place, and minus 3 over 4 ln y is equal to ln x plus c. Now, some of us might be wondering, why is it that I only add the integration constant to the right hand side and not to the left hand side? So it's not any problem anyway. If I decide to speak literally, is not a big problem. You can as well add an integration constant to the left hand side, that is the y side, if you want, but conventionally we just add the integration constant only on the left hand side. If someone wanted to still go ahead and add the integration constant on the left hand side, this is what he's going to get. For instance, you integrated the left hand side, right? And perhaps you wanted to use, let me say, a b as your constant. Then you have your ln x plus c. You can still simplify it like this. is equal to lim x, then plus c minus b, like this. So since c and b are both arbitrary constants, so we should expect that c minus b would be another arbitrary constant. So we can say c minus b evaluates to a. So one thing about arbitrary constants is, since we are working with them, we can there's lots of random assumptions. You can call one arbitrary constant another arbitrary constant, and you can just twist the shape, twist the form, and however you want to put it. Okay, so c minus b is an arbitrary constant. Now when you compare this solution with this solution, you will see that it's not different from each other. It's just in the choice of the symbol that you used for arbitrary constant. But looking at these two equations, clearly they both have one arbitrary constant. So whatever your arbitrary constant is, your arbitrary constant may be different from another person's own. Nobody told you which arbitrary constant you should use. In fact, you're allowed to use any symbol that you want to use for arbitrary constants. But let it just be that we can see one arbitrary constant in your solution. So remember what we said about first order differential equations, okay, that they have just one arbitrary constant. So this is the case now. We are seeing that arbitrary constant, and if you differentiate this equation again, you are going to solve it and you're going to get back this differential equation that was given to us in this problem over here. So you're going to get back this differential equation. Okay, so this is the first example. I hope it will throw more light into what we're going to be doing next. So let's tackle problem 2. Welcome to problem 2. So we're going to be as fast as possible. Now you can see that problem 2 is not just a question, is actually an IVP. So this is an IVP. Okay, alright, so IVP meaning it's an initial value problem. We are given a differential equation and we are given some initial conditions. Y of 0 equal to pi over 4. So what does y of 0 equal to pi over 4 means? Y of 0 equal to pi over 4 means that when y is pi over 4, x is 0. Okay, so whatever will be in this particular bracket, you should save it for whatever it's going to be in this bracket, save it for the independent variable, okay, which in this case is x. So they're just trying to tell us that the value of y has a solution corresponding to pi over 4 radians when x is actually 0. Is that okay? So let's try to solve this differential equation and see the outcome. And just to refresh us before we dive into the problem, the essence of giving an IVP or giving initial conditions is to help us determine what the arbitrary constant is. Okay, just take note of that. Now let's begin to solve this problem and let's see how to go about it. So we have cos y plus 1 plus exponential minus x sine y dy dx, is equal to 0. So if you can look at this problem critically, you discover that we can actually carry out separable variable technique here. Okay, so this is how it goes. For this particular differential equation, I'm going to send cos y to the right hand side like this: 1 plus exponential minus x sine y dy dx is equal to negative cos y, like this. Then if you separate the variables, or if you take everything about y to the left hand side and everything about x to the right hand side, so you're going to get sine y over minus cos y dy is equal to 1 over 1 plus e to the minus x dx, like this. Alright, so Let's see where this leads us to. So we are going to integrate both sides now. Integrating, we're going to have integral. So let me just leave this as minus sine y over cos y dy is equal to 1 all over 1 plus e to the minus x as integral dx. So how do we go about with integrating this particular problem? You still have to remember the quotient rule of integration as for this particular left hand side. So the LHS quotient rule of integration. Then for this right hand side, so we are going to also apply the quotient rule of integration, but we are going to modify it first. Now let's do that together. Now you agree with me that the left hand side, if you look at it critically, on the denominator we have cos y, while on the numerator we have minus sine y. Now minus sine y dy is still going to be written as d cos y, right? While on this particular right hand side, if we multiply every term by exponential x, we're going to get exponential x all over, then 1 times exponential x is exponential x, and exponential x times exponential minus x, they will cancel out to give you exponential 0, and exponential 0 is 1, so dx, like that. So you've modified the form of this particular one. Some of us will be wondering how did this particular left hand side, how did this become d cos y? Actually, I can write it like this: 1 over cos y d cos y, alright, is equal to integral of exponential x over exponential x plus 1 dx. So how did this particular place become d cos y? You just have to remember, assuming you want to differentiate with respect to y, cos y, if you still remember, you get minus sine y. Is that okay? So we have d of cos y is minus sine y dy. So whenever you see minus sine y dy, you can leave it as d of cos y. Now this approach of solving your problem is important because you can now see this particular left hand side as if you were integrating something like this: 1 over x dx, okay, 1 over something d, that same thing. Is that okay? And when you integrate 1 over x dx, it gives you ln x. Okay, now I'm going to apply it to this particular left hand side. So this should give me ln of cos y, right? Ln of cos y is equal to, then the same thing applies to the right hand side. How do we particularly integrate it? How do we particularly integrate this particular expression? Well, if you observe very, very carefully, if you differentiate the denominator, okay, assuming the denominator is given to me as let's say I want to differentiate the denominator with respect to x, what will I get? I'll still get exponential x. So invariably d of exponential x plus 1 is equal to exponential x dx. So I can now replace this exponential x dx here with d of x plus 1. Is that okay? So you have integral of, on the numerator you will have 1 e to the x plus 1, then instead of exponential x dx we'll have d of exponential x plus 1, like that. So this is still corresponding to the general form, integral of 1 over something d something Okay, and this should give you ln of that particular something, ln of something. So in writing the answer for this particular one, you're going to get ln cos y is equal to ln exponential x plus 1, and we can now put our constants of integration. So we are now going to continue manipulating the solutions in this form. So we're going to take the exponential of both sides, okay, or before we do that, I can say ln cos y minus ln exponential x plus 1 is equal to c. So if you apply the law of logarithms to the left hand side, you have ln cos y over exponential x plus 1 is equal to c. Then what do you do next from here? You can now remember ln is still the same thing as log to base e. Okay, so we have log to base e cos y into exponential x plus 1 is equal to c. So the implication is cos y exponential x plus 1 is equal to exponential c. And exponential c, just like c is an arbitrary constant, exponential c can also be another arbitrary constant. So exponential c can be equal to a. Is that okay? So we can actually use this convention. Exponential c is equal to a. They are still arbitrary constants literally. So we have cos y over exponential x plus 1 is equal to a. So this is a solution, or a possible solution, or someone can see that cos y is equal to a exponential x plus 1 like this. So this is another way of writing it. Now let's go ahead and apply the IVP that was given to us. The IVP was y of 0 is equal to pi over 4. So remember we said that this means when y is pi over 4, x is equal to 0. So let's go ahead and apply and see what we're going to get. So applying this, you have cos pi over 4 is equal to a exponential 0 plus 1. Remember that cos pi over 4 is still the same thing as cos 45, which is 1 over root 2. And you have a into what? Exponential 0 plus 1, and which is 1 plus 1. So we have 1 over root 2 is equal to 2a. So 1 over root 2 equal to 2a means a is equal to k, 1 over 2 root 2. And if you rationalize 1 over 2 root 2 times 2, or let me say root 2 over root 2, you're going to get root 2 over 2 times root 2 all squared, which is equal to root 2 over 4. So all we now have is our cos y is equal to root 2 over 4 exponential x plus 1 like this, or y is equal to cos inverse of root 2 over 4 into exponential x plus 1. So you can actually leave your answer like this. So the initial value problem has converted the look or the outcome of our solution from one having an arbitrary constant to one where we have just a solution without arbitrary constants. So we use the initial value problem, that's given initial conditions, to determine the value of the arbitrary constant. So thank you for staying tuned up to this point. So I'm going to look at another example shortly. Okay, here we are at problem 3x cubed plus y plus 1 whole squared divided dx equals to 0. So this is clearly variable separable. So how do we know x cubed plus y plus 1 whole squared divided dx equals to 0? So you can write it in this way. Dy is equal to minus x cubed. Then you can now say y plus 1 whole squared dy is equal to minus x cubed dx, like this. So how are we going to approach this one? So we can just integrate both sides. Integral of y plus 1 whole squared dy is equal to minus integral of x cubed dx. You can still leave it like this. So how do we integrate this one? So we're still going to use our technique. Alright, so remember that you can see in this particular left hand side you have y plus 1 whole squared dy. You want to integrate it. So just recall that had it been you want to differentiate y plus 1 with respect to y, all you're going to get is 1. Is that okay? So in other words, d of y plus 1 is still the same thing as dy. So I can actually replace this integral to look in this form. Instead of dy, I can use d of what? Y plus 1, like this. Okay, because d of y plus 1 is equal to dy. So if we integrate this side according to our law of integration, we'll have negative x to the 4 over 4 plus c. Is that okay? So let's keep solving. So when you want to integrate this one, take note, it now looks like this form: integral of something square d something, and this is something cube over 3. Is that okay? According to the literal meaning of our integration. So this now becomes y plus 1 cube over 3, right, is equal to negative x to the 4 over 4 plus c. So if we multiply both sides by 3 and 4, multiplying both sides by 12, we are going to get 12, which is the LCM in this case. Multiplying through by 12, we are going to get 4 y plus 1 whole cube and is equal to negative 3 x to the 4 plus 12c. So 12c can still be a, for instance, because c is an arbitrary constant. So 12c is another arbitrary constant. Let's just call it a. So 4 into y plus 1 whole cube, plus 3x to the power of 4 is equal to a. So this is the solution for this particular problem. There was no initial conditions given, so this is our general solution in this particular case. So for this problem, this is the general solution over here. So the general solution is a solution that has an arbitrary constant inside of it. So general solution is an arbitrary is one with an arbitrary constant, while a particular solution is a solution whereby we have applied initial conditions and determined the value of the arbitrary constant. So we have general solution and particular solution. Please take note of those terminologies. We'll be using them more frequently in ordinary differential equations as we proceed in the future. So let's go on to another problem. Alright, we're given this particular problem and we want to solve for the solution of this particular problem definitely you agree with me that this is an IVP, initial value problem, because we have the differential equation given to us here, then we also have initial conditions given to us here. So let's figure out together what the solution is going to be. So to figure out the solution, it's still separable variable technique that we're going to use. dy dx is equal to x squared y. So all you just need to do is to, of course, separate the variables. So 1 over y dy is equal to x squared over 1 plus x squared, like this, and dx. Okay, so I hope you understood this transition. You just separate the variables and take note of where each variable is supposed to land at whenever you separate it. Each variables have a place where they will land at, whether the numerator or the denominator. Just be mindful of where they are going to stay. Okay, like this y was on the numerator on this particular right hand side, but once it transitioned into the left hand side, it became on the denominator, and this guy was on the numerator on this particular side, but once it transitioned to the right hand side, it became on the denominator position. So we can now integrate from this point. Integral of 1 over y dy is equal to integral and x squared over 1 plus x squared dx. So how do you solve this problem? The left hand side is easy, quite frankly, because you're just going to get ln y. Okay, so the problem is, how do I go about with the right hand side? Okay, so before I write anything here, you have to use, okay, let me just write it, x squared over 1 plus x squared dx. So you can now consider this fraction, polynomial fraction. Okay, this polynomial fraction can actually be reduced to a more simpler form when we use long division. So if we use long division, we're going to get 1 x squared taking into x squared, like this. So x squared into x squared is 1, right? 1 times x squared is x squared, and 1 times 1 is plus 1. So by the time you subtract two of them, x squared minus x squared is 0. There's already a 0 here, so 0 minus 1 is minus 1. So the remainder is minus 1. Is that okay? So this particular fraction, x squared over 1 plus x squared, is still the same thing as you having how many whole number? You have one whole number, and we now have minus 1 over 1 plus x squared. This is literally equal to 1 minus 1 over 1 plus x squared. Okay, if you evaluate it, you will get the same thing at the end of the day. So we have actually taken care of the form of this particular fraction. So we have ln y equal to integral of 1 minus 1 over 1 plus x squared dx. So if we carry out the integration, we'll have ln y is equal to, integrating 1 with respect to x, you get x, and if you integrate 1 all over 1 plus x squared, if you check your tables, this is tan inverse of x plus c, constant of integration. So remember, this is an IVP, so we're giving y of 1 equal to 2. So if we are given this particular initial condition, y of 1 equal to 2. What are we going to do with it? It means that y is 2 when x is 1. So we have ln 2 is equal to 1 minus tan inverse of 1 plus my constant of integration, right? Then if you solve for the IVP, if you solve, you get ln 2 equal to 1 minus tan inverse of 1 is pi over 2, pi over 4 at 45 degrees, then plus c. So we have c is equal to ln 2 plus pi over 4 minus 1. So that's the value of c. This is problem 5, which is just almost equal to what we have in problem 4. So we want to solve 1 plus x cubed, okay, multiplied by dy dx, then it is equal to x squared y, and y of 1 is equal to 2. So similar approaches, dy dx, is equal to x squared y. So what we are going to do is still the same. 1 over y dy is equal to x squared all over 1 plus x cubed dx when we separate the variables. Alright, so after separating the variables, we are going to integrate. Integrating, so the left hand side evaluates to ln y, and the right hand side will still remain like this for now. Okay, so now we want to integrate this particular left hand side. So remember that trick that we've always been looking at from the start. Assuming you want to differentiate 1 plus x cubed, what are you going to get? You're going to get 3x squared. Isn't that right? So in other words, d of 1 plus x cubed is still the same thing as what? 3x squared dx. So if there's a way I can modify this particular right hand side such that I can introduce a 3x squared dx into this particular place, so that I will be able to replace 3x squared dx with d of 1 plus x cubed, then I will be able to integrate with my normal simple principles of integration in this way. So the ln y is equal to, assuming I introduce a 3x squared, right, I have to counter the effect of introducing that 3 by adding the reciprocal of 3. Of course, a number multiplied by its reciprocal is 1. Then you have x cubed dx. So at this point now, we can now see ln y is equal to 1 over 3 of instead of you to have 3x squared dx, you're having 1 over 1 plus x cubed, then d of 1 plus x cubed. Are we together? So since you have the right hand side to be like this, you agree with me that the answer after integrating will be ln 1 plus x cubed plus c. Okay, so assuming we multiply through by 3, we'll have 3 ln y is equal to ln 1 plus x cubed plus 3c, okay, and let 3c be equal to d, for instance. So this 3 ln y can be the same thing as what? Ln y cube, according to the law of logarithms. So you have a ln 1 plus x cube plus d. Now see what happens when we take the exponential of both sides. So taking the exponential of both sides, you're going to get exponential ln y cube is equal to exponential ln 1 plus x cube plus d. So this right hand side is still exponential ln 1 plus x cube dot exponential d. If you remember your law of indices, okay, a raised to the power of m plus n is equal to a raised to the power of m dot a raised to the power of n. So that's what is playing out here in this particular place. So you should also remember another important identity, that's exponential ln f is equal to f, okay, courtesy engineering mathematics by K. Stroud, then and the general mathematical principle. So exponential ln y cube is y cube, then exponential ln 1 plus x cube is still going to be 1 plus x cube, and exponential d can be a constant a, for instance. So y cube is equal to a into 1 plus x cube. Is that okay? So this is supposed to be how this problem arrives at its solution. So this is general solution. So we were given the IVP that y of 1 is also 2. So since y of 1 is 2 in this particular equation, then you have to actually apply the values. Remember, y is equal to 2 for x equal to 1. So 2 cube is equal to a of 1 plus 1 cube. So 2 cube is equal to a of 2, and a is equal to 2 cube divided by 2, which is equal to 2. 3 minus 1 equal to 2 raised to the power of 2 equal to 4. Or 2 cube over 2 is actually 8 over 2, which is 4. So y cube is equal to what? 4. Sorry about that. 4 of 1 plus x cube. Or someone can say y cube minus 4 into 1 plus x cube is equal to 0. So this is your particular solution, and this is your general solution. So the general solution, like I said before, is the solution that you obtain when you leave your expression of y in terms of arbitrary constants. But your particular solution is the solution that you write when you have found the values of the arbitrary constants with the initial conditions that you were given. So let's go on to another example. Okay guys, welcome to problem 6 and the last for variable separable methods. So let's look at what we have here. Of course, you can see that this is just a product of x and some x function and some y function, then some y function and some x function, and we have our dy dx equal to 0. So to separate the variables, as usual, we'll have x squared y plus 1 the bracket plus y squared into x minus 1 dy dx equal to 0. So first of all, y squared into x minus 1 dy dx is equal to negative x squared into y plus 1. So if you separate the variables, we will get y squared over y plus 1 dy is equal to minus x squared over x minus 1 dx, like this. So we have separated the variables. Okay, so this should be a trivial step for you. So just split whenever a term in the numerator crosses the equality, it becomes a term in the denominator, and vice versa. Whenever a term in the denominator crosses an inequality, it becomes a term in the numerator. In other words, it is reciprocated. Then you are going to integrate y squared y plus 1 y, while at the same time integrating negative x squared over x minus 1 dx. So let me just better still write it in this form. Is equal to negative integral of x squared over x minus 1 dx. So we are going to do something now with this integral. So consider y plus 1 y squared and x squared over x minus 1. So we are going to use long division, because if you want to integrate something like this, remember this is kind of like improper fraction, so you have to like divide it to its lowest terms, that you have it in terms of the standard fraction format, which makes it easier for us to integrate. So we are going to carry out long divisions on these fractions, okay, to simplify the process of integration. So starting with y plus 1 into y squared. Now y into y squared, of course you know, is y. So y times y is y squared, and y times 1 is y. So take note of the 0 here. Y minus y is 0, and 0 minus y is minus y. So it can still be divided, in the sense that y can still go into minus y to give me minus 1, and minus 1 times y is minus y, and minus 1 times plus 1 is minus 1. Take note of the 0 here again. So we are subtracting. Minus y minus minus y is 0, then 0 minus minus 1 is 1, like this. So you're going to repeat the same process for x minus 1, okay, and x squared. So x into x squared is x, x times x, x squared, and x times minus 1 is actually minus x. So when you subtract x minus x is 0, then 0 minus minus x is x. So x into x is 1, and finally 1 times x is x, 1 times minus 1 is minus 1, so that x minus x is 0, then 0 minus minus 1 is actually 1. So this is what we have concluded from the long divisions, that y squared over y plus 1 is equivalent to y minus 1 whole number, y minus 1 whole number, 1 over y plus 1. Okay, so this is a plus 1 as from this place, and at the same time we have x squared over x minus 1 is equivalent to x plus 1 whole number half plus 1 over x minus 1. Now this is still the same thing as y minus 1 plus 1 over y plus 1, and here it's still the same thing as x plus 1 plus 1 over x minus 1. So you should remember that 2 whole number 1 over 2 is still the same thing as 2 plus half. So that's the concept I'm using to analyze this particular one over here. So since we have gotten the corresponding breakdown, we can now go back to our integral. So instead of integrating y squared over y plus 1, we are integrating y minus 1 plus 1 over y plus 1 with respect to y. And at the same time, we are integrating minus. We have x plus 1 plus 1 over x minus 1 with respect to x. So continuing on with our integration, we are going to have y squared over 2 minus, integrating 1 you get y, then when you integrate 1 over y you get plus ln y plus 1, okay, then is equal to minus, you get an x squared over 2 plus an x in this case, then plus ln x minus 1, and what do you have over there? Your constant of integration plus c. Okay, so when we solve further, because it's good to leave your answers in good form, you have minus x over 2 minus x minus ln x minus 1 and plus c. So I'm just going to take all the variables to the left hand side and leave the constants on the right hand side. This is another cool way of leaving your answer. So you have y squared over 2 plus x squared over 2, then you now have minus y, then plus x, and plus ln y plus 1 plus ln x minus 1, and is equal to c. Okay, so we just took everything about variables to the left hand side, and we left the constants on the right hand side. We can also say y squared over 2 plus x squared over 2 plus x minus y plus ln, applying the law of logarithm, y plus 1 multiplied by x minus 1. Okay, so this actually works like this, is equal to c. So if you happen to multiply everything by 2, let me just arrange it in this form. I'll have x squared plus y squared plus 2x minus 2y plus 2 natural logarithm of y plus 1 and x minus 1 is equal to 2c. So you can let 2c be a, for instance. So you have x squared plus y squared plus 2x minus 2y plus, you have what, 2 ln x minus 1 sorry about that, y plus 1 is equal to a. So I think we can stop here. So this is the answer to this particular problem. So this brings us to the end of separable variable problems. Remember, like I said earlier, all other differential equation problems will definitely lead you to a point where you will have to apply the method of separable variables, and you will now have to integrate, then find the general solution like we're given here. Or if they give you an IVP, so from your general solution you're going to substitute your initial conditions so that you can be able to determine your particular solution. So thank you for watching this long series. If you actually made it to the end, then I celebrate your passion to learn. Please, if there's any questions or anything you don't understand, drop it in the comment section. Feel free to reach out. Don't forget to like, share and subscribe, hit the notification, bells to stay updated. So see you in the next class, where we'll begin to understand linear differential equations and in the terminology called integration factor. So take care till then.